A magnitude 7.0 earthquake just hit the South Shetland Islands, just off the coast of the Antarctic Peninsula. Almost nobody lives there. There are no cities, no civilian infrastructure, but this is exactly the kind of event that grabs the attention of seismologists around the world because of where it happened and what it tells us about what's moving beneath the ice. The quake was shallow, roughly 10.5 miles deep. That's critical. Shallow earthquakes concentrate their energy close to the surface, which means stronger local shaking, greater seafloor displacement potential, and more intense effects at the epicenter. In a region already defined by fractured, overlapping tectonic boundaries, a release this large demands close attention. In this video, we'll look at why this location matters, what kind of fault system produced this quake, what new maps have revealed about the hidden continent buried beneath the ice, and what all of it signals about one of the most geologically complex plate boundaries on the planet. The South Shetland Islands sit between the Antarctic Peninsula and the Scotia Sea, straddling a plate boundary where the Scotia Plate interacts with the Antarctic Plate. This is not a simple, clean fault line. It's a zone where the crust is being pulled apart, shifted sideways, and compressed in different places simultaneously. The broader boundary is primarily transcurrent, dominated by lateral, sideways plate motion. But near the South Shetland margin, the picture becomes more complicated. There's an old subduction trench offshore. There's active extensional deformation in the Bransfield Strait, the narrow waterway between the islands and the peninsula, and there's volcanic and magmatic activity in parts of the system. This layering of tectonic processes, old subduction, present-day strike-slip motion, local rifting, and volcanic influence, makes the South Shetland region one of the most structurally complex plate boundaries on Earth. A single large earthquake here doesn't come from one simple fault. It comes from a system of interacting faults, each with its own geometry and stress history. A shallow magnitude 7.0 beneath the ocean immediately raises the question of tsunami potential. The answer depends on the fault mechanism. Transcurrent, sideways motion is generally less efficient at generating destructive tsunamis than thrust faulting, where one plate is shoved beneath another and the seafloor lurches vertically. Classic megathrust subduction earthquakes like the 2011 Tohoku event in Japan displace enormous volumes of water precisely because the fault rupture drives the ocean floor upward. The South Shetland region's boundary is predominantly strike-slip, which reduces the tsunami risk compared to a pure subduction zone. But this area is not purely strike-slip. The old Shetland Trench and the Bransfield extensional system add a vertical component to some faults in the region. Until a reviewed focal mechanism is published confirming the exact fault geometry and slip direction, tsunami risk cannot be fully dismissed. Initial monitoring has not indicated significant wave activity. Given the remote location and the likely predominantly lateral motion, a major tsunami is improbable from this specific event. But the complexity of the tectonic setting means that the standard assumptions about what a magnitude 7.0 does or doesn't produce needs to be checked against the actual data, not assumed from the magnitude alone. The South Shetland Bransfield system has a well-documented history of seismic unrest. Historically, seismicity maps show dense clustering of past events throughout the region. Between 2020 and 2021, an extraordinary earthquake swarm struck the area, linked to deformation near the Orca Seamount and structures within the Bransfield Basin. That swarm wasn't random tremor activity. It was associated with magmatic intrusion, molten rock pushing upward through the crust, stressing and fracturing surrounding rock as it moved. The South Shetland Islands host volcanic systems, and past swarms in the border boundary zone have been directly connected to subsurface magmatic processes. This does not mean the current magnitude 7.0 is volcanic in origin. A single large tectonic earthquake is not evidence of an impending eruption. That determination requires separate indicators: volcanic tremor on seismographs, surface deformation measured by GPS or satellite radar, changes in gas emissions, or a swarm pattern specifically clustering beneath a volcanic center. None of those signals have been reported in connection with this event so far. The stronger assessment is that this was a major tectonic release along one of the faults in the Scotia Antarctic boundary system. Significant but consistent with the kind of activity this region has always produced. Enjoy deep fact-check space stories? Hit subscribe and activate the notification bell. Otherwise, YouTube will not show you the next videos, and you'll miss what we uncover next. Earthquakes like this one remind us that Antarctica is not just ice. There's an entire continent underneath, and until very recently, we knew less about its topography than we do about the surface of Mars. In January 2026, a team led by researchers at the Université Grenoble Alpes and the University of Edinburgh published the most detailed map ever produced of the landscape buried under the Antarctic ice sheet. The study, published in Science, used a method called ice flow perturbation analysis. Instead of drilling through the ice or relying solely on airborne radar, the team analyzed high-resolution satellite imagery of how the ice surface moves. Every undulation, every slight variation in flow speed carries information about the terrain below. The way a bedsheet draped over furniture reveals the shapes underneath. What they found was far more complex than anyone expected. Buried under an average of 1.2 miles of ice, the map reveals mountain ridges, over 30,000 alpine valleys, vast plateaus, and a channel stretching roughly 250 miles through the Maud subglacial basin. In East Antarctica, canyon systems plunge as deep as 11,500 feet below sea level. Many of these features were completely unknown before this study. Much of this hidden landscape dates back more than 34 million years to a time when Antarctica had a temperate climate and no ice at all. A global cooling event driven by declining atmospheric CO2 triggered the formation of the ice sheet, which eventually buried nearly the entire continent. What remains underneath is essentially a geological time capsule, an ancient terrain preserved under miles of frozen water. The discovery matters beyond geology. The shape of the bedrock beneath the ice directly controls how fast glaciers flow toward the ocean. Valleys channel ice and accelerate it. Ridges slow it down and act as natural barriers. Without knowing where those features are, climate models can only approximate how the ice sheet will respond to warming. With this new map, researchers can identify which regions of the ice sheet are most vulnerable to accelerated loss and refine predictions for sea level rise. If the entire Antarctic ice sheet melted, global sea levels would rise by roughly 190 feet. That is not a realistic near-term scenario, but the study underscores a more immediate concern. Even modest increases in ice loss, guided by the hidden topography now being mapped for the first time, would be enough to threaten coastal regions worldwide. The bedrock determines where the ice is strongest and where it is most fragile. And now, for the first time, we can actually see that distinction in detail. So, when a magnitude 7.0 earthquake shakes the South Shetland Islands, it is not shaking empty ice. It is shaking the edge of a continent with mountain ranges, deep valleys, and vast channels hidden beneath its surface. A continent we are only now beginning to see clearly for the first time. A shallow magnitude 7.0 earthquake will produce aftershocks. Some of them will be strong, potentially magnitude 5 or above, and they can continue for weeks or months. Monitoring agencies will be tracking the sequence closely. The key data point still outstanding is the focal mechanism solution, the analysis that reveals the exact orientation of the fault and the direction of the slip. If it confirms predominantly strike-slip motion, the event fits neatly into the regional pattern of lateral plate movement. If it shows a significant thrust or normal faulting component, the implications for seafloor displacement and the broader stress picture change. Additionally, any reports from Antarctic research stations regarding local shaking, intensity, infrastructure damage, ice slope instability, or unusual wave activity will help define the real-world impact of this event. In a region this remote, hard confirmations take time. The USGS has reported the event between magnitude 6.6 and 7.0. Other monitoring networks have it at 7.0. Final magnitude determination typically stabilizes within hours to days as more seismographic data is processed. What is already clear is that this was a major earthquake on an active, complex plate boundary. The South Shetland Scotia Antarctic junction is one of the most tectonically intricate regions on the planet, and it just produced a reminder that the forces beneath the ice are anything but dormant. A magnitude 7.0 just shook one of the most remote fault zones on Earth, but three far more populated fault systems in North America are quietly building toward their own inevitable rupture. The question is, which one goes first? Watch San Andreas versus Cascadia versus New Madrid. Which mega quake will strike first to find out.